talk, this might be the time. So to all those who are live and all those who will watch the attended version, welcome to the LIDS seminar. Today's LIDS seminar is held by Professor Michel Delfour. And Michel is a professor of mathematics and statistics at the University of Montreal. He has authored or co-authored lots of books and lots of papers. You can look at the numbers online if you want. And Michel has actually a longer history with LIDS. I think Michel did his PhD with Professor Sanjay Mehtar back in the day. And in case, maybe Sanjay wants to share a couple of words if he wants, but just wanted to mention, I saw Michel's research spans a variety of areas, including shape and topological optimal design, analysis and control of delay and distributed systems, and many things related to differential equations. And he has a variety of honors. He's a fellow of SIAM, he's and of the Canadian Mathematical Society and the Academy of Science at the Royal Society of Canada, and also formerly the Guggenheim Foundation. And today, in particular, we're excited to have Michel here teach us about Hadamard semi-differential calculus. This, in fact, is a very important topic in non-differentiable optimization or building the foundations of non-differentiable optimization. And I'm actually really looking forward to learn this material from Michel, because he also has a very accessible book on this topic. So in case, Sanjay, you want to say anything, I'll hand over the command to you. If not, then the floor's Michel's.
Michel, nice to see you. Can you hear me?
Yes, yes, Sanjay, no problem, I hear you.
Good to see you and looking forward to your talk.
Okay.
Okay.
Thank you very much.
Okay, so without further ado, then Michel, it's all yours. Thanks.
Okay, first, all my thanks to Sanjay and the team that running the seminar. I am sorry that I could not come, that I didn't come last time, but I think it was the good decision because of the pandemic. So I'm still in good shape. Maybe that's the reason. Okay, today, the topic looks a little bit abstract for an engineering seminar. But in fact, it's the result of work I've done with Zolisio, and we have used this Hadamard semi-differential for shape optimization. And recently, since I was teaching to undergraduates, I tried to push this point of view in my course, and over years it ended up in a book that second edition just came out with SIAM. Now, the benefit of waiting since March is that I have been able to go through all the notion of Hadamard semi-differential that were given in finite dimension to go to topological vector space, which I knew it could be done, but now it's done. And there is a recent paper which appeared a few days ago in the Journal of Pure and Applied Functional Analysis. Okay, so I think that's it. I think I will just give you the menu. I hope to be able to cover everything, but as usual, I might have too much material. So we are going to go quickly over the differential in Euclidean space, finite dimension, then go to topological vector space, and then relax all that to semi-differential, in which case we're going to tackle non-differentiable problems. And at the end, I have a few examples. The first one is within the context of MIT. It is the Danskin-Burt-Sekas theorem. You have an example from plasma physics, and then shape and topological derivative. Good. So The right definition of differential that was not obvious at the time, and we can find a trace of that in the Austrian Stolz, an American, Pierpont, an Englishman, William Henry Young, and a Frenchman, Fréchet. But it seems that according to Tiomirov, that the one who most likely gave the right definition the first time was Karl Weierstrass in his lectures in Berlin. Because the lectures were only published in the 30s, and the lecture, of course, were given before his death in 1897. It's clear Stoll had a scholarship to go to Berlin to work with Weierstrass. Pierpont, after his PhD, went to Germany. And Young, that's another story, that he went to Germany with his former student, Grace Childon, who had a PhD with Klein. Okay, now, I'm going to start with the definition of Fréchet because it's the one I like, which is more compact, more analytical. But the other definitions were equivalent to this one. So this is the classical definition you find in any good book in analysis. And I'd like to first make this remark. If you take a sequence Tn, a real number going to 0, a sequence Wn going to V, then the product goes to 0. And if you form this differential quotient, you discover that this goes to dfxv, dx being the linear mapping here, so that this thing is true. And you obtain another definition of differentiability, which for the moment I call M differentiability. Okay, I will explain where the M comes from later on. So Fréchet implies M. Now, the third definition that came from Hadamard in 1923, and it is in the paper of Fréchet, it is described that way. And I like this because it's exactly the way I was introduced to the total derivative when I was young at school. So you take a function f on R2, you give increase in delta x, delta y, so that gives you an increase in the function. And then you rewrite this in the sum of two terms. You sort of assume that these differential quotient go to some limit. And you have this expression. And I'm pleased that Hadamard questioned the meaning of that frame expression. Because for me, delta x going to 0, this should have been 0, 0, 0 everywhere. So what he says is that there is something missing. There is an auxiliary variable which is missing. So think of t like a real number, like a time, if you want, and h of t as a trajectory through the point xy. The notation h may not be the best one, but that's the only one I had left to work with. So h of t is a trajectory. H, it goes to xy, and there is a tangent to that trajectory, x prime, y prime. Now, if you compose f with h and take an ordinary derivative in 0, you get this, and by putting everything together, it's the gradient inner product with the tangent to the trajectory h. That is the interpretation of Hadamard. So it gives you the following definition. So you define admissible trajectory at x as a trajectory going to x such that there is a tangent at the point x. And then the Hadamard differentiability at x, you assume that there is a linear mapping, dfx, such that for all admissible trajectories, this derivative of the composition exists and is equal to df x h prime 0. So it's really a geometrical definition of the differentiability. Now, if f is n-differentiable, the previous definition I had on the other slide, and you look at the any admissible trajectory. For any sequence, you form the sequence of the quotient, differential quotient, that goes to h prime 0. You rewrite this in this way, and htn is x plus tnbn. But since it is m differentiable, this goes to this limit after x applied to h prime 0. So you have Fréchet implies m differentiability, implies Hadamard differentiability. Now, in dimension 1, in dimension 1, yes, yeah, okay. In dimension 1, those three definitions, they coincide. So Fréchet, and differentiability, and Hadamard. And we are going to work with these three notions in topological vector space. And by the end, what we will see is that the one that will remain is Hadamard. Okay, there is a weaker notion that of directional derivative that goes back to Volterra and the beginning of the calculus of variation. So I'm just including that here. So the Gateau directional derivative. So it's weaker than the M derivative because the T, there is no variation in the V. There is just one limit with respect to T. And T goes to 0 by positive or negative value. And of course, when you have linearity, that's the classical Gateau differential. So this is very weak. All the rules of the differential calculus are verified, except the chain rule. And also, this function is not necessarily continuous. And the example, there are many examples. That's the example I like very much. This is a function which is Gateau differentiable everywhere. The gradient is 0 in 0, Gateau gradient, but this thing explodes. And of course, the chain rule is not valid. So this is not a very good notion of differential. Okay, so let's jump to topological vector space. Not quite. The first one is Fréchet. So the first the definition he gave for finite dimension was 1911. Now, 14 years later, he gives the same definition, but in norm vector space. Later, let's see, 13 years later, I think it's Michael, could be Michel, I don't know. Michael gives a notion of topological differential. And the idea was to relax the norm in the definition of Fréchet. Good. Yeah. Okay, don't be scared, but that's the definition. Not it. It's usually say that this was not very popular as a definition, but it does the job. There is this special function epsilon of a two variable v1, v2, and it has to satisfy all these conditions. To make it more easy to understand, if f is Fréchet differentiable, that mysterious function epsilon is given by this expression. And in fact, if it's Fréchet differentiable, it is M differentiable in the sense of Michel. Okay, let's continue. Now, again, I'm going to consider this differential quotient for the M differential that I defined earlier. And it turns out that if it is M differentiable in this sense, which is not obvious, then you get M differentiability. So this M differentiability of Michel is between Fréchet and the n differentiability I defined earlier for in the finite dimensional case. So be careful, there is an ambiguity in the terminology, but I explain why later on. Okay, now Fréchet again, he generalized the notion of Hadamard differential to topological vector space in 1937. So it's the same definition of an admissible trajectory with a tangent, and it's the same definition of the Hadamard differential. Now, just I want to emphasize the fact that here you assume that there is a linear mapping, and we will discover later on as a consequence that this mapping is continuous. In finite dimension, it's obvious, but in topological vector space, Fréchet had to assume it, but here you don't need to assume it, it will be free. Michel, 1938, that is 1 year later, gives a definition he calls HM differentiability, probably for Hadamard Michel, but that definition is the one of completely equivalent to the one of Fréchet. So there is nothing new here. Okay, now let's go to semi-differential. And the first interesting event is, again, Fréchet. And Fréchet, in the 1937 paper, he drops the condition that the function d be linear and replace that by a function of v. And if you use the same definition, you discover that, of course, you can multiply t by alpha t, and you get a new trajectory. And the result is that you have alpha times the tangent. So you get a whole tangent, a whole line tangent to the trajectory. And then using the definition, I will skip the steps, you discover that this function is homogeneous. For the gradient, you have something linear. Here, you have something homogeneous. And you push his case further. He gives an example. So this function is differentiable everywhere except in 0 at the origin. And at the origin, you can show that in the direction VW, it is equal to the function f in VW. And this function is homogeneous and continuous. This initiative was strongly criticized by Hadamard. Hadamard always insisted on the fact that the differential should be linear. He was also criticized by Paul Lévy. Alors, Paul Lévy, look at it. Hadamard was the grandfather, Fréchet was the father, and Lévy were the sons, if you want. So he was very close. Unfortunately, he didn't pursue because he could have catched the norm and the convex functions. And I explained that here why. If you look at the norm, which is not differentiable at the origin, his new definition fails. If you take an admissible trajectory such that the H prime exists, you form the differential quotient. And unfortunately, here you get the absolute value of t over t. This converge, but this diverge. However, if you had chosen a half trajectory, something from 0 to t with a right-hand side derivative, that this thing exists, then when you form the differential quotient, the problem here disappears, and since you have right-hand side derivative for this, and you have the norm which is continuous, you get it. You get the differential, which is not linear. And here the positive homogeneous function is v going to the norm of v, which is positively homogeneous and continuous. So he was very close, you see. Sad. So let's do that for him. So we introduced the notion of semi-trajectory, which are admissible. So from 0 to tau with a half tangent in 0. And then the definition is the same. So for the composition, the right-hand side derivative exists and is equal to this function for a fixed v, whatever be the admissible trajectory which is chosen. And of course, if it's true for all v, you say that it is semi-differentiable. You said that it is differentiable if this function of v is linear. So that's neat. And now you can catch the norm. Okay, that brings us to Penaud, Jean-Paul Penaud. I think it's 1978. And he's the one who introduced this notion of M semi-differentiability, which gives the confusion with the definition of Mitchell. But he used the M for Mitchell. Let's see, his definition is for a direction V, you want this limit, double limit, to exist. It's exactly the definition I gave at the beginning in a finite dimensional case. And of course, if it's true for all V, it's semi-differentiable. And if you have the linearity, you say that it is differentiable. Here, all the rules of the classical calculus are valid, including the chain rule. That's important. The same thing was true for Hadamard also. So why did he use that letter? I think this definition is really due to Penaud, and somehow I cannot extract this definition from this the definition of Michael with the epsilon, unless someone can show me how to do it. But so it should have been called Penaud derivative. Okay, now where I am, yes. The M semi-differentiability turns out in topological vector space, turns out to be stronger than Hadamard. But there is something, you can weaken that definition of M semi-differentiability. Instead of having V, all the W going to V, you do it only for sequence. So if you have a direction V, there exists this dmfxv, such that for all sequence Pn converging to V, this limit exists and is equal to that. And so on, MS semi-differentiability. Okay, so what you discover, always in topological vector space, is that this MS semi-differentiability is equivalent to Hadamard semi-differentiability. Of course, if you're in a Fréchet space, Hadamard, MS, everything coincides. And the bonus is that you have a complete differential calculus. So the first result is that with respect to the direction V, this mapping is positively homogeneous, but it's also sequentially continuous. You have all the rules of the calculus, including the chain rule. There is another property missing, is for a differentiable function, usually it is continuous at the point where it is differentiable. And that comes from this theorem under at least unexpected condition that there exists a bounded neighborhood of the origin. Don't forget, you're in a topological vector space, so that's quite general. And in a given topological vector space, the neighborhoods of the origin need not be bounded. So if there is one, then the function is sequentially continuous. Of course, if the space is Fréchet, everything coincides. And I think, yes. Okay, I think it's a good point to make another remark, because you see this sequential continuity arise several times. And when you think about sequential continuity in a topological vector space, so you have sequence xn going to x, and then f of xn goes to f of x. In fact, it can be given in terms of semi-trajectory. You have a semi-trajectory converging to the point x. You don't assume that the differential quotient exists. And the continuity of f composed with the semi-trajectory at x, going to fx is equivalent to sequential continuity. So the definition, this definition of Hadamard semi-differentiability is really a sequential definition of differentiability in topological vector space, of course. Good. Now we are going to specialize Lipschitz continuous functions. So if this is the definition of Lipschitz at a point x, so there is a neighborhood, a ball, where the function is Lipschitz. I'm going to use the Gateau semi-differentiable function. So here I relax the t goes to 0 by positive value. And what you get is that if in norm vector space, of course, to get the Lipschitz property, if the function is Lipschitz at x, and if it is Gateau semi-differentiable, then it is M semi-differentiable. So it's a lot easier to check Gateau semi-differentiability than M semi-differentiability. So that covers quite a large class of functions. And now we not go back, we go ahead, go to real valued function and convex functions. Well, there is, to be convex is a very, very, very strong property. In fact, it's equivalent to small I and 2i. But the most important property is that this Gateau semi-differential exists for all points in the convex and all directions. That's a key point. And then if you add continuity, to such continuous functions, then if f is continuous, you're in a locally convex topological vector space. If f is continuous, then f is M semi-differentiable. If f is sequentially continuous, then f is Hadamard semi-differentiable. And of course, in a Fréchet space, everything coincides. So it's very, very strong to be a continuous convex function. And if you go back to norm vector space, then all these notions are equivalent, f bounded above, f Lipschitzien, Hadamard semi-differentiable, continuous, and even just Hadamard differentiable in the direction 0. Good. Yes. Okay. Now, the last test. That is, now we are going to consider function defined on an arbitrary set. The first motivation is really first to look at function defined on embedded submanifold of Rn, but it applies to any subset of a topological vector space. So, if you have a smooth embedded manifolds, here it's a curve, a smooth curve. If you usually the set is equal to its boundary, And if it's smooth, then you have a linear tangent space. Now, if there is a kink, well, there is a problem because if you look at trajectories, you obtain only two directions. So it's a cone, it's not convex, and you have to work with that. If you have a function defined on this at this point, the best you would get is a directional derivative here in that direction. Okay, so let's see what kind of cones is available in the literature. So there is the Boulingin contingent cone, but it's not really the one which will be well suited for our purpose. It's the adjacent tangent cone. And the difference between the two cones is this. Here there exists a sequence, and here for all sequence. So the T flat is really the interesting cone. So. Yeah. So we generalize the definition of an admissible semi-trajectory. So now you have a set A. The M differential, that doesn't work, but Hadamard works because it works with semi-trajectories. So you're looking at the trajectories in the set A, and you assume that the right-hand side different derivative exists. So there is a half tangent to this half trajectory. And the interesting result is here, is that the adjacent tangent cone, the T flat here, is the set of all semi-tangent to all the admissible semi-trajectory in A at X. That's where the connection is. And now we are going, with this, we will be able to extend the notion of Hadamard without introducing local bases, coordinate space, and the approach is different from the one of Michel and Fréchet, who independently extended that to function defined on a topological abelian group. Yeah, okay, so now the definition is the same as before, except that you take direction in T flat of A. So there exists a DHFXV such that for all admissible semi-trajectory H in A at the point X with a semi-tangent equal to V, this exists and it's equal to DHFXV. So, and this, if it's true for all direction in T flat A, then it's Hadamard semi-differentiable. And you say it is differentiable if first the tangent cone is a linear subspace and the function V, dfxv, is linear. And that gives you a function from TB flat at A to its image, from cone to cone. Now, let's see, do we still have our differential calculus? Do we still have the continuity, or sequential continuity? And the answer is yes. So we go from A to X, function A to Y, sorry, and in the direction V. Then this map, V, DHFXV, with respect to the direction from the one cone to the other cone, is sequentially continuous for the induced topology and positively homogeneous, obviously. Then you have your calculus, again, linear combination of function, linear combination of semi-differential, and you have the chain rule, everything you wish for. And now there is a continuity of the function at the point x, and this you also get. I was going in the right direction. Yeah. Okay. So again, if there exists a bounded neighborhood of 0, f is sequentially continuous at x in A for the induced topology on A. And of course, if it's Fréchet, everything is continuous. So it's absolutely fantastic. It's complete. So you can do a semi-differential on manifold, smooth manifold, or manifold that are not smooth at all. The worst thing that can happen is that your tangent cone T flat be just 0, in which case there is little interest in looking for a differential or semi-differential. Okay, I must include this slide for people interested in non-smooth analysis to emphasize the difference between Hadamard and, for instance, the work of Clark. If you have a Lipschitzian function, there is a notion of strict differentiability, which is I use the definition from Borwein-Lewis. So instead of looking everything at x and making the direction move, now the point y is moving towards x. This definition is stronger than Fréchet. And there is an example that I will skip because you can find that on the slide. And then what is done, for instance, by Clark is to relax the limit to the lim in for the lim sup. You can do the same thing also with Hadamard. Instead of a limit, you can put a lim in for lim sup. What is happening is that you lose completely your differential calculus in doing that. And to fix that, you have to go to sub-differential. And of course, that's nice. There is a nice geometrical way of doing these things. Okay. Yeah. Now, yes, so I emphasize the fact that continuous convex function, you can get them by Hadamard. And finally, it's a matter of choice, you know, which calculus you are going to use. And I'd like to quote something from Maurice Fréchet, a quote I like very much. It's about a new, more general definition of differentiability by Paul Lévy. See, lastly, the definition due to Mr. Paul Lévy, not necessarily verifying the theorem of composite function, the chain rule, is still more general, but for this very reason, perhaps too general. Okay. Let's go to the example. I don't know how I'm doing with time. Okay, it's still good. So it was a must to talk about the Denskin's theorem here. So I think all of you know it, but so you have a function of x and y. You minimize with respect to y. Y is a compact, and you have this function g of x, which is equal to the infimum. Y of x are the minimizing point in y. And then I went over the proof in Denskin, and in fact, you can repeat all the steps. But with Hadamard, you get something more at the end of the exercise. You get that, in fact, the G is Hadamard semi-differentiable, which means the chain rule applies to those functions. And of course, you get all the other continuity. Similarly, now you go to the generalization by Bertsekas, by Dimitri, to convex or concave function. Here I chose the concave case in order to stay with the infimum. And essentially, I have nothing very extraordinary to say, except that at the end, you conclude that this thing is Hadamard semi-differentiable, and then you can compose that with other Hadamard semi-differentiable functions. In his proof, Dimitri is using a theorem from Rockefeller. So I had to go to Rockefeller, and I found the theorem. And when you go to the proof, you notice that by the end of the day, you have something a little bit stronger that is Hadamard, not just directional derivative. So that's one. The second one is plasma physics, the Grand-Mercier equations. And that's not recent, that was done in the 70s. Théman, well, Grand-Mercier equation, Théman worked on that in 77 with his student Mossino. And then Mossino and Zolesio came with a variational version of this. So this is the equation. That is, you have a Laplacian, and you have here a term which is non-local. That term is here. You take the function u at the point x, and you look at all the points such that u of y is below u of x. So it's a set, and you take the measure of that. So that's a non-local function. And this is that equation. U is normalized flux of electron. And don't ask me too many questions about that. I don't really master the physics behind that. But if you introduce this function, so the first part is something standard. It's quadratic, linear, good. And then you introduce this other term, which is the term which is convex, non-differentiable, but continuous, for which the Hadamard differential exists. Then you can show that there exists a solution to this minimization problem. You can show that the solution is unique. And since you have a non-differentiable term here, you have a necessary condition which takes the form of an inequality. And you can look at this function. So it's linear in U, here, linear in V, sorry. This is also linear in V, but this is the trouble term. But you can extract from this equation, this one, plus something else, and a bonus. This is the set of all y in omega such that u of y is equal to u of x. That is, all the y which are on the level set u of x, which means, saying that this is a zero, it means that the function u cannot have a plateau. A plateau which is of non-zero measure. So it's quite remarkable to extract from this convex function this kind of information. Okay, now, time is going down. Now, let's go to shape derivative. Here, the setup is the following. You have a family of sets, and you want to deform the set in order to get something which is a derivative with respect to the shape of the set. To do that, the thing to do is to use a diffeomorphism. So you have the set, you apply that to the set. So the image of the set is another set, but it's not just any set. You cannot create whole, you cannot create connected component. you can only deform the set. That's why it's called shape derivative. So you need a group of diffeomorphisms. And this was done by Anna Maria Micheletti, an Italian. I'm not sure, she might have been done a doctorate with someone at the Scuola Normale or at the University of Pisa. She was a professor at the University of Pisa. And that's the group she introduced. So bijection says that F minus identity is CK0. CK0 are the transformation from Rn to Rn, K times continuously differentiable and going to 0 at infinity. And what is really remarkable is that she constructs a metric that makes all this a complete metric space. And in 2000, when we looked at this, her paper, that it took a lot of time before we discovered that she had done the right job. Her construction is generic. That is, you can replace this by, for instance, Lipschitz continuous function or other spaces of transformation. And what you find is that when you look at the tangent space at each of these diffeomorphisms, it's equal to the whole space, theta. So the tangent space is linear space, so it's a Finder manifold, and you can define a shape derivative. Well, I don't know how much detail I should go because I'm afraid I will try to lose you, but let's see. So the velocity method that was created in '79 by Zolesio, what it does is that you look at the family of velocities, v of t depends on t and x. You look at the differential equation, the solution of that differential equation, from which you construct a transformation Tt of Rn. So those Tt, they are the diffeomorphisms. And if you choose them CK, they will be in the group of Micheletti. Now, if the Vt go to 0, so the Vt, the velocity, are the tangent to the group of Micheletti. And so you have trajectories in the group of diffeomorphism, and the derivative, the right-hand side derivative of the path, the trajectories, is V0. So this has exactly the structure which we have described earlier. Well, just maybe if you look at this last line, if you have just an integral of omega, f over omega, you perturb with the diffeomorphism. And the end result is something which is an integral over the boundary of f, normal component of v. Okay, the topological derivative is a little bit more difficult to swallow, but let's do it. Okay, here the group that is involved is the group of characteristic function of Lebesgue measurable sets, which is a subset of L infinity Rn. And the group operation is the symmetric difference, which amounts here for the characteristic function, the absolute value of the difference. This group operation, the empty set is a 0 set, and chi of omega is its own inverse. So this topological group and so forth. Now you're interested in the tangent to that group. And let me explain a little bit what the topological derivative is. You have a set omega. You take a point here. You dilate the point, a small ball around the point. So Now the perturbation of the set omega is omega minus that bar. And you want to know the variation of your cost function with respect to the radius, for instance, of this bar. That's typically. So here you see it's a topological perturbation because you're creating a hole in the set. Now, if you do so, you construct chi omega minus the dilatation. And in fact, all this is connected to the Lebesgue differentiation theorem, because if you subtract the k omega minus ER minus k omega in a weak sense, you divide by the volume of the ball. The Lebesgue differentiation theorem tells you that this is equal to minus phi of E. And this is the delta function minus the delta function in E. So the tangent space to that group contains bounded measures. Now, in fact, if I want to connect this with everything I've said before with a trajectory that depends on T, the T that you have to choose here, it's not the radius of the ball, but the volume of the ball. And if you relabel everything, you can repeat the exercise and you have a weak derivative of the characteristic function, which is equal to the delta minus the Dirac delta function. Okay. You can multiply the T by rho, and you discover that you have minus rho delta function. And also the thing which is important is that you don't have a full tangent, you have a half tangent. So here, your tangent space is not a linear space, it's a cone. Okay, now we'll go quickly. So this was a perturbation of a set at a point by creating a hole around the point. Now I can do that also with a curve. I have a curve, for instance, in 3D, and I dilate the curve. I can do it with a piece of surface in 3D, the same thing. And in fact, you can perturb your set with what Federer called derectifiable sets. That is, sets that are the image of a compact set in RD, 2x. So pieces of curve, rectifiable surface, they can be used. Here there is an example. You have a circle in 3D. You dilate the surface, it becomes a torus. And finally, you have a measure, and the measure is the integral over E, the curve. And here you have the Hausdorff measure of dimension 1 coming up. This replaces the delta function. Okay, so I think you can create a new connected component like that by dilating this and so forth. So I think I will conclude because it becomes too technical. Those interested can look at the slide. So the conclusion is that Hadamard semi-differential functions are quite nice. I hope I convinced you. I think it's probably the largest family of non-differentiable functions for which the classical differential calculus and the chain rule are preserved. Of course, it includes continuous convex, concave, semi-convex function and all that. And because of its geometric foundation, as you've seen, the Hadamard semi-differential calculus extend to function defined on smooth embedded differential submanifold and simply subsets not only of the Euclidean space, but the topological vector space. Okay, for shape, you have metric groups and everything works. As I said earlier, it has a very large intersection with what people are doing in non-smooth analysis, but the two are not contained into one another. So there is an intersection, but they don't cover the same thing. Now, the last thing I'd like, that's almost a project, but I have the feeling, and maybe only you who are in statistic data analysis can answer that question. Could this be pertinent in probability statistics data analysis? The reason why I say that is, for instance, in the case of a topological derivative, now we are working in space of measures. We are working with subsets of sets. Like in probability, you have set of events and you have probability cylindrical measures. So I have the feeling that maybe this could be of interest to you. And I think, yeah, yes, okay, I'm within the time. And I thank you for your attention. Here you have a long list of reference at the end. Oof.
Can we ask questions?
As far as I'm concerned, yes.
Okay. I had to unmute my computer. Michel, a very nice and comprehensive talk that goes way back. I noticed, however, that you did not mention at all the work of Mordukowicz and the work of Rockefeller and Wetz on variational analysis, which relates closely to Mordukowicz's work. And so how would their work fit into the overall landscape that you presented?
Well,
you mentioned the work of Clark, of course. You did mention the work of Clark.
Sorry?
I wanted to say also that you did mention the work of Clark, which is related, but the work of Mordukowicz and Rockefeller and Wetz is supposed to be more up-to-date, more definitive, in some circles anyway. So I wonder if you can comment.
Yeah, okay. So essentially, I started from the book, finite dimensional book, and what I presented you today is a little bit abstract in the fact it's in topological vector space. So I didn't really went beyond that. I was concerned with getting all the proof of the theorem one after the other. I have to look at other work. Now that I know all this, it's clear that there must be connections. Unfortunately, I must confess that I don't know all the work, and I was trying to stay away from everything using sub-differentials. Okay, so it's not a school bias. It's I'm talking about what I know, and I would be very much interested that you communicate those this work to me. Because here I'm looking for other connection with other discipline or work. Is it really satisfying answer?
Well, there are connections, and a lot of work on non-smooth analysis deals with extended real valued functions also. take the value plus infinity. And I think you focused on the real valued case, right? The real valued functions.
Yes, because if you want a differential and if you want to have the differential calculus, you cannot play with functions that go to infinity. So you have to make a choice. In fact, I could have used as the title of the talk, how to preserve the chain rule.
Yeah.
See, that was really the motivation. Try to stick to our calculus as much as possible and see how much we can catch from nonlinear problems. And clearly at this stage, everything that goes to infinity is out of bound.
There are chain rules in convex analysis, but I agree they are more complicated. They involve, they are more complicated.
They involve sub-differential.
Sub-differentials, yes.
I mean, there is a whole class of variational problems arising in image analysis and vision, typically in functions of bounded variation and so special bounded variation where you throw away the contour set. So it would be interesting to look at those variational problems as calculus and what role semi-differential functions play. So I would say that in image analysis and vision, this theory should have broad applicability.
Yes. Yes, I agree. It's in image processing, at least the theoretical part of it, the work that did the Italian, it's clear, their application, but shape and topological stuff, this is very much related. Of course, we are far from all the algorithms that you have to develop. It's topological vector space. It's a little bit too general, but the structure is there. I hear someone.
Okay, so I don't have a question, but rather to say that your host, Suvrit, had to leave just as you were concluding your talk. So I guess I'm putting myself in his shoes. Well, thank you very much for giving this talk. It's refreshing in a way to go back to the classics and put our feet on the ground again. If there are no other questions, I guess let me just thank you very much for being with us.
Thank you also.
I guess there is no